Hi everyone, my name is Jingyan, and today I'm going to discuss our work on thinking about mitigating sequential bias in evaluation. This is joint work with Ashwin Pananjady at Georgia Tech. Here we are considering a set of high-stakes decision-making problems where the goal is to estimate the quality of a set of items. By sequential bias, we mean the evaluation outcome depends on the ordering that items appear. There is a lot of empirical evidence to suggest sequential bias actually exists in many applications, such as court decisions, loan applications, and various competitions. Now let's look at one concrete example from the literature, and this is a Queen Elizabeth competition. This is a music competition, and in the last round, there are always 12 finalists. They appear in an ordering that is uniformly at random. So as the competition begins, the first person comes, they perform, and the judge gives a score to the first person. Then the second person comes, the judge gives a score to the second person. And this process repeats for all the future candidates in the competition. In this paper, the authors, they look at the historical data and count the number of winners appearing at each of the 12 positions over the years. I'm making some simplifications of what they actually did, but roughly speaking, they look at the number of winners at each position, and they observe an increasing trend of the sequence of numbers, which says if a candidate appears later in the sequence, it's more likely for them to win. So this is the type of sequential bias we are thinking about here. In this paper, we address two questions. The first is how do we use a mathematical model to describe the sequential bias? And given the model, how do we correct for the bias? We'll start with the first modeling question. The goal of modeling is to mathematically describe how the judges they give scores in a way that explains the existence of the sequential bias. Let's think about why this bias arises, and we believe one of the reasons is the judges, they are gradually adapting their grading scale based on the previous items they've seen. And because of that, they have strictly more information when they are scoring later items. This creates an asymmetry and hence the bias. For example, let's say the judge has some internal scale of the items. When the first item comes, we don't really know how this item compares to others, so we just place it roughly in the middle and give it some score accordingly. However, when the second item comes, we have a point of comparison, which is the first item. Here, we use the area of the square to represent the quality. The bigger the square, the higher, the better the item is. So here, item 2 is lower than item 1. We'll place it on the scale somewhere to the left of item 1 and accordingly give a score to the second item. Similarly, when the third item comes, now we have 2 points of comparison, which are item 1 and item 2. In this example, item 3 is in the middle in terms of its area. So we place it in the middle and accordingly give a score to item 3. And this process repeats for all the future items. This insertion model is based on this assumption that the scores are given based on some relative reasoning and comparison from the judges. And there are a few reasons why we made this assumption. First, the scores are often explicitly defined by relative measures. Here, I'm showing the instruction given to reviewers for New Rift 2016, where a score of 5, for example, means this paper is the top one among 1,000 submissions, and a score of 4 means this paper is placed on the top 3 of all the submissions, where the current paper is compared to all the submissions to this conference. Also, based on social comparison theory, people evaluate others and themselves in this comparative manner rather than an absolute manner, and this theory has some evolutionary origins. There is also this exemplar model of memory, which says the knowledge of people is represented by the previous items they've seen, which are called exemplars. So when people are applying their knowledge to score the items, implicitly they are comparing to some items in their mind. Mathematically, we assume there are n items in total. We say item T has a relative rank of RT, which means this item is RT's largest among the first T items so far. Here, we assume a higher rank means the item is better. For example, let's consider time step 3. If the third item is below both item 1 and 2, then its relative rank is 1. If it's in the middle, the relative rank is 2, and if it's higher than both, then the relative rank is 3. At each time step, we compute the relative rank of the current item, and these relative ranks are fixed for each item. So as the time progresses, we don't update previous values of the relative ranks. They are fixed at each time step. We assume the judge gives a numerical score to the item, where, again, the higher the score, the better the item is, where the score is the sum of two terms. The first term describes some internal process of the judge, which depends on the position T and the relative rank of the item R of T. So F describes how the judge maps the information so far to a numerical score. And then we add a standard noise term on top of F. The first question is, how do we model this function F? We'll derive a function F, which we show is the optimal response of the judges in a particular sense. Specifically, we consider the goal of the judge as achieving perfect calibration, which means if an item T is above 60% of the population, then ideally the judge wanted to give a score of 0.6 to this item. We assume the judge minimizes the squared error between their scores and the true percentage of each item, which is perfect calibration. And we sum the squared error over all the items. We show the theorem that says if the true ordering is uniform at random, then if the judge's goal is to minimize the squared error, their optimal response is to give each item T a score of this form, which is R of T divided by T plus 1. Let's look at how this model works with an example. Here, let's say the first item comes, its relative rank is trivially 1 because there are only one item so far. So its score given by the judge is 1 divided by 1 plus 1, which is 1/2. We have more items coming in, item 2, 3, 4, and let's look at item 5, where the relative rank of item 5 is 4 because it's the fourth largest, like it's above 3 items in the sequence. So the score given by the judge is 4 divided by 5 plus 1, which is 4/6 or 2/3. Here we see the issue where item 1 is higher than item 5 in reality, but item 5 receives a higher score. This aligns with what we see from the music competition, where the probability of winning is increasing for items at later positions. Now let's look at some intuition why this function F takes this particular form. Let's think about the case for item 1. When item 1 arrives, let's think about how each of the feature items compare to item 1. There are two possibilities, either they are below or they are above. And because the true ordering is uniform at random, by expectation, roughly speaking, half of them are below and half of them are above. So the optimal response of the judge is to say item 1 is in the middle and give it a score of 1/2. Similarly, let's consider item 2. Let's assume item 2 is lower than item 1. And we consider how each future item compares to both item 1 and item 2. There are 3 possibilities. Either an item is lower than both, or in the middle, or higher than both. Again, because the true ordering is uniform at random, roughly speaking, each case happens with probability 1/3. So the optimal response of the judge is to give it a score of 1/3 to item 2, meaning we believe item 2 is above 1/3 of all the other items. Here we talked about item 1 and item 2 separately, and one key part of the proof is to make sure the optimal response is independent over time step T. In addition to justifying the model using this optimal response property, we also conducted crowdsourcing experiments where we recruit workers from the online platform Prolific. We present each worker a sequence of circles with different sizes. And again, we tell them the larger the circle is, the better it is. And we instruct the workers to classify these circles into 10 decils in the same online manner, where, for example, the bin of 0 to 10% means the item is the lowest 10%, and the bin of 90 to 100% means the item is the top 10%, etc. We collect data from this experiment, and here I will only mention one piece of the experiment. In this experiment, we present workers this ordering shown on the slide, where, again, there is this inconsistency between item 1 and item 5, where item 1 is lower, but it receives a higher score as predicted by the model. So we compare the score given by the workers to item 5 and item 1, and we see a significant fraction of them, that is 163 of the workers out of 200, they do give a higher score to item 1 than item 5. So this aligns with the model and also the previous empirical studies. I invite you to see more results from the experiments in the paper. Let me pause here and summarize what's discussed so far. We propose an insertion model for the scoring process that is motivated by psychology and empirical studies. The particular function F is the optimal response for rational agents if they wanted to achieve perfect calibration, and we also conducted crowdsourcing experiments to further verify properties of the model. So far, we've been taking the perspective of the judge. The judge, they observe items so far, and their goal is to predict perfect calibration. Now we are switching gears. We take the perspective of the audience. We no longer have the expertise to judge the items. So we only rely on the scores we see from the judges, and from the scores, we estimate the ranking of the items. Now I'll discuss our algorithm for ranking estimation and also the theoretical guarantees. Let's recall N denotes the number of items in the sequence. We use pi star to denote the true ranking of the items, which means item T has a true absolute ranking of pi star of T. So pi star is an n-dimensional vector. We assume the judge gives a score y of t to each item T according to the proposed model F. And our goal here is to estimate the ranking pi hat from the scores y. Here, we assume this ranking is done after we see all the scores. So even if the scores are given in this online process, we are doing this estimation as a post-processing offline. We first consider a naive baseline, which is just to use a ranking induced by the scores. This means we collect the scores for the items and sort these scores in the increasing order. That's the order we give to the items. This is also what's happening in competitions. We've already seen the problem with this approach, which is the scores, they are now consistent with the true ranking. What's the issue with this induced ranking baseline? And intuitively, it's because the relative ranking, they don't always reflect the absolute ranking. Because of this online process, the judges, they only see the relative ranking, and they derive their scores using this function F. And the induced ranking tries to infer the absolute ranking directly from the scores that are based on the relative ranking. Instead, our algorithm is also simple, where we just recover these two steps. In the first step, the function F maps from the relative rank R of T to the score Y. So we just take the inverse and we compute the relative rank from the score, and we can do this perfectly in a noiseless case. And in the second step, we run the insertion sort procedure where we iterate over all the items, and for each item, we insert it to the position according to its true relative rank R star of t. It's quite simple to see both steps are perfect in the noiseless case, which shows our algorithm is always correct. The challenge here is to extend this algorithm to the noisy case, because now with the noise, we cannot perfectly reconstruct the relative rank, the insertion under the noise. Instead, we consider a least squares estimator where we are iterating over all the possible ranking pi, and we compute this error, which is the square difference between the observed score y of t and the noiseless scores according to the function f if the true ranking were pi. We compute the square difference and we sum over all the items. However, here a second challenge is enumerating over all the possible rankings takes exponential time. And we'll see an algorithm that combines the two ideas of insertion and least squares, which overcomes these two challenges. Specifically, we propose a noisy insertion algorithm that solves the least squares estimator exactly in near linear time. The way this algorithm works is we still use the insertion sort procedure, but now we can now compute the exact relative rank R star of t. We estimate a rank R hat of t based on what the least squares estimator instructs us to do. This is the algorithm. And for theoretical results, here in the noisy case, we assume the magnitude of the noise is bounded with this parameter delta. So delta is like the noise level. But what otherwise we allow the noise to take any arbitrary value. We assume the true ranking pi star is uniformly at random, and we consider the expected error where the expectation is taken over the true ranking pi star. We consider two standard ranking metrics from the literature. One is the Spearman's foot rule, which is the L1 distance between the estimated ranking pi hat and the true ranking pi star. We also consider the worst case error, which is the max error of this difference vector. We normalize both metrics so that their values lie in between 0 and 1. We derive theoretical results that says for both metrics, Spearman's foot rule and the worst case error, our algorithm achieves an error of at most order delta, where on the other hand, information theoretically we show any estimator incurs an error of order at least delta. So this shows the optimality of our algorithm up to log factors. Here, the error is linear in parameter delta, which is a noise level. So as delta goes to 0, our algorithm incurs 0 noise and gives the perfect result, which recovers the noiseless case I showed. But now here, the error is 0 on any random ordering as opposed to the worst case ordering. Finally, we provide simulation results where we assume there are 30 items in total. We generate noisy scores for these items according to the proposed model F. And in this plot, we show the error for the item at each position. And we see for items appearing at earlier positions, for example, the ones in the red circle, we see the ranking error is significantly reduced by our algorithm compared to induced ranking. This suggests our algorithm is also more fair for the items that appear early. I also invite you to see the paper for additional simulation results. To summarize, in the second part, we discussed this noisy insertion algorithm, and we show theoretical guarantees to show this algorithm is optimal. For future work, our framework actually allows us to incorporate prior knowledge into the model. Essentially here, we assume the judge already has some exemplar items before they start scoring the first item. So in practice, this prior knowledge is unknown, and we have thoughts on how one might learn this prior knowledge from the data and we'd like to work out the details. Second, it's an interesting question to design multiple rounds for the competition. Here, we are allowed to choose an ordering for the next round based on the scores we already collected from the previous round. So it's an online design problem. And finally, in the experiment, we showed a linear scale of 10 bins, but we can actually consider more sophisticated data elicitation schemes where, for example, we can design an adaptive rating scale joining with a sequential model. It could be the case that in the beginning, the judges, they don't have much information. So it makes sense to use a cohort scale versus towards the end of the sequence, the judges, they have more information. So maybe it's better to use a finer scale at that point. I'm happy to discuss more about this work on email, and thank you for listening to the talk.